Great. So I'm continuing with my Halloween colors, and I'm on 1.38. So 1.38 says we're going to look at some equations. So 1.38. And we're going to determine if these equations are possible by looking at the dimensions. And it says v is speed, a is acceleration, x is distance. Anything with a subscript of 0 means a quantity at time 0. So the first equation I get is x equals vt squared plus 2at. Now, to be dimensionally consistent, the dimensions on the left-hand side, which is x is distance, so that has dimensions of length. Velocity, I'm going to put in brackets, is L t minus 1. Time is t, it's t squared, plus 2. Well, the 2 doesn't matter because it's a proportional constant, so we can get rid of it. The coefficients don't have a dimension. Now, a is meters per second squared, so that's length time to the negative 2. Length per time squared. And then a time. So what we'll do here is we need the left and the right side to equal. So if I use my rules of exponents, I get L times t plus L t to the minus 1. And here we have a problem. These can't add, and I have t units where I have no t on the right hand side. So this can't be an equation. Can't be an equation. It's not valid physics because my dimensions don't mask. So we're using the definitions for each of these variables that are given, and our variables are representing something. And we want to see the dimensions. So we'll look at equation B. We're going to use the same process, equation B. And so we have x equals v naught times t plus 1/2 at squared. So again, on the left-hand side, we have length. V naught is meters per second, length per unit time, right? Length per time. Remember I said I'm a big fan of keeping my negative exponents. You can think of this as L over T. Time has units of time. Now for the 1/2, it's constant, so it has no dimensions. A, if we look back up at the top of the problem, A is meters per second squared, or length time to the negative 2. And then this time is t to the 2. So we have L, t negative 1 times t. So the exponents will leave me with L here. And t to the negative 2 times t squared leaves me with L. Now, this isn't an addition and an algebraic sense, and I would love to have some symbol here to represent it. It might be proportionality will help, but I can add when my dimensions are the same. So an L plus L will give me dimensions of L. And so this is valid equation. And that's how dimensions work. Remember, the terms in an addition have to have the same dimensions. If they don't, you can't add them. And the example I like to say is like if you have a length per unit time, like a velocity, and you try to add that to a distance, that's like saying 60 miles per hour plus 5 miles. Doesn't mean anything. But in this case, we have a length plus a length. So, 5 miles plus 4 miles. You get 9 miles. You get returned a dimension of miles. And that's called dimensionally consistent. Alright, so let's look at C. We're playing the same game. And we're given the equation, let's let's see, x equals v naught times t plus 2at squared. Well, what we want to do here is we could really look between the last two problems and note that term is the same. So we know this term is going to come out to L. We're going to use the work that we did before to save us some problems. And if we look here, the only thing different is that constant. Well, constants don't have dimensions, so this dimension is also L. So this is valid. And you should be looking for these things to save time when you're comparing results. Not because time is what you want to do, but what you want to really be able to do is look at what have I done before? How can I use what I've done before? And not just in the sense of problems. When you look at an acceleration times time squared, you should be thinking length. Now, this doesn't have to be automatic or happen with every problem you do, but this is a pattern that'll extend. And so it's good sometimes to compare one problem to another, because if they're the same, you can get to the same process more quickly. And if they're different, you should be looking at why they're different. A lot of what we're doing when we map reality into equations are we're trying to find things where we can use the same process. And to see that pattern, comparison helps. And so when I was doing this problem, I said, well, this looks really, really similar to the equation above it. And well, oh, only the constant's different. And so, well, do constants have dimensions? No. So these problems must have the same dimension. And that's a valid way to think, and it's a good way to think because it's economical.